So you are welcome. Today our discussion is on DC circuit, resistors, and application of Kirchhoff's law on this kind of circuit. So let's delve into it. Resistors. So a resistor is an electrical component that limits or regulates the flow of current in a circuit. So when we have a circuit, a resistor present regulates the amount of current that flows through the circuit. It controls and regulates the amount of current in the circuit. So the current through the resistor is therefore giving us voltage over the resistance. So the voltage provided in the circuit over the resistance of the resistor gives the current flowing through the resistor. So if you look at the diagram here, we have a resistor, we have a voltage source, and the current passing through. So if you want to know the amount of current that the resistor can take, then we divide the electromotive force or the EMF by the resistance of the resistor to get the amount of current passing through the resistor. Now we will talk about connections of the resistors in the circuit. And the first connection we'll talk about is the series connection. So in the series connection, the resistors are connected end to end. So they are connected in line from one end to the other. They are connected in line. And the current within the resistors are the same because the amount of charges passing through them is the same. So in the same time interval, the amount of charges passing through all the resistors are the same. And the potential difference across the resistors are not the same. Therefore, their sum gives the total potential difference across them. Their sum gives the total potential difference across them. So if you look at the diagram here, the resistors are connected end to end. The resistors are connected end to end. Therefore, having the same amount of charges and current passing through, but with different potential difference. So we sum up the individual potential differences to know the total potential difference across the resistors. So now, for us to know the total potential difference, as I said earlier, we sum up all the potential individual differences that they have. So we take R1, then you find the potential difference. We take R2, then you find the potential difference. Since the current through is the same, that's why you have an I. But they're having different resistances. So R1 have the resistance, R2 have the resistance. We sum them up to get the total potential difference across them. Now, the equivalent resistance of the resistors in series is the algebraic sum of the individual resistances of the resistors. So if you want to get the total resistance we have in the circuit, we therefore sum the individual resistance. So it's a direct summation. We just sum them up to get the total resistance in the circuit. Now, resistors in parallel. So in parallel connection, the potential difference across each resistor is the same because each is connected directly across the battery. So each resistor has its terminal connecting directly to the voltage source. Therefore, they're having the same potential difference across them. But the current through each resistor is not the same because the current spreads out when it reaches a junction, as we will see in Kirchhoff's law. So the current entering the junction will be the same current leaving the junction. Therefore, for us to get the total current, we sum the current leaving the junction, then we equate to the current entering the junction. So the current entering the junction must be equal to the current leaving the junction. So we know that from Ohm's law, our current is voltage over resistance, as we've seen earlier. So for us to get the potential difference, for us to get the current flowing through all the junctions we have in the circuit, we sum up the potential difference, which is the same for all the resistors, over the resistance 1, the resistance 2. So if you look at this one here, when the current gets to point A, it will spread out. So we will be having I2, then I3. So for us to get the current passing through the resistors, we sum this current up, then we sum this current up to give us the current passing through the resistors. Now the equivalent resistance is giving us 1 over RQ all over 1 over R1 plus 1 over R2 plus 1 over R3. So for this one, the resistance, the equivalent resistance is the inverse of the resistances. So we sum them up by taking the inverse of the resistances to get the equivalent resistance. So if you look at the diagram here, as we discussed earlier, when the current gets to this junction, it spreads out. So some will pass through I1 and some will pass through I2. And when you sum these two currents, they should be equal to I1. from Kirchhoff's law. Now, each resistor operates independently. Each resistor operates independently, and all resistors operate on the same voltage. So each resistor is independent and they operate on the same voltage. The current takes all the path that we have in the circuit, as I said earlier on. So if there are numerous junctions we have, when the current reaches that junction, it will breaks out and separates through all the path that it creates in the circuit. The lower resistance will have higher current, and even higher resistance will have some current passing through. So if you have a resistor with a high resistance, no matter the amount of resistance the resistor has, there will be some amount of current passing through the resistor. Now let's look at the Kirchhoff's law. So there are ways in which resistors can be connected so that the circuit formed cannot be reduced to a single equivalent resistors. So the Kirchhoff's law is used here, and there are two laws that can be used. The first one is the junction rule, and the second one is the loop rule. So let's go into detail and see this kind of laws and how they are applied in the circuit. So for the junction rule, the rule states that the sum of the current entering any junction must be equal to the sum of the current leaving that junction. So we saw earlier on that when the current is entering the junction, it should be equal to the current leaving the junction. So mathematically, the sum of the current entering the junction should be equal to the sum of the current leaving the junction. And this statement proves conservation of charges. So I1 is entering the junction, and it should be equal to I2 plus I3, because I2 and I3, they are the ones leaving the junction. So this is the junction rule. Now the loop rule. This rule states that the sum of the potential differences across all the elements around any closed circuit loop must be zero, and it is a conservation of energy statement. So if you sum up all the potential differences across all the elements in the circuit, their summation should be equal to zero. So mathematically, the summation of all the potential differences in a closed loop is equal to zero. So traveling around the loop from A to B. In this diagram, traveling from A to B, meaning you are traversing around an element in the circuit. So from figure A, the resistor is traversed in the direction of the current. And the potential difference across the resistor is minus IR. So if the resistor is traversed in the direction of the current, the potential difference is negative. If it is traversed across, or if it's traversed in the direction of the current, the potential difference across the resistor is negative. Now, if in figure B, if the resistor is traversed in the direction opposite to the current, that is, if we have our loop from A to B, whilst our current is moving from B to A, then the potential difference across the resistor will be positive. So we should take note of that. If the current is moving from B to A and our loop is from A to B, you are traveling from A to B, you are traversing through the resistor from A to B, then our potential difference across the resistor will be positive. Now in figure C, so from figure C here, the source of the EMF is traversed in the direction of the EMF. So if we are moving from A to B and the direction of the source of EMF is from negative to positive, then our electric potential will be positive. If we are moving from A to B, so from this diagram, if we are moving from A to B, as in the loop, if we are moving from A to B, and the source of EMF is from minus to positive, then the change in potential is positive. But if we are moving from A to B across the EMF source, and the EMF source is moving from plus to minus, then the potential difference or the change in potential is minus. So take note of the difference. If you are moving from A to B across the EMF source, and the EMF source is moving from plus to minus, then the change in potential would be negative. The change in potential would be negative. Now, some tricks in solving problems relating to Kirchhoff's law or circuit with a lot of loops. In a problem solving, the circuit must be drawn. So the circuit diagram should be drawn. We assign labels and symbols to all the known and unknown quantities. Then we assign the directions to the current. So we are supposed to show us the direction of the current through the circuit. Then we assign all the labels to the known and unknown quantities in the diagram. Then we apply the junction rule to any junction in the circuit that provides new relationship among the various currents. So any junction you see in the circuit, you are supposed to apply the junction rule to it. Then you apply the loop rule to as many loops as are needed to solve the unknowns. The loop rule you apply must be significant. So you are supposed to apply all the loop rule that you will use to solve the problem to find out the unknowns. So to apply for the loop rule, you must correctly identify the potential difference as you cross various elements. So you are supposed to know the potential difference as you cross various elements before you apply the loop rule. And the direction of traversing the loops must be consistent. So the direction at which you are traversing the loop must be consistent. Then you solve the various equations that you derive from the loop rule and the junction rule that is applied simultaneously to get your unknowns from the problem. So let's look at an example, then know how to apply the rules to all the junctions and the loop that you get in the diagram. So the question is, find the current in the circuit below by using the Kirchhoff's rules. So here is our diagram. So in our diagram, here is our first loop. And our first loop is moving from A to B. So if you can see the arrow, it is moving from A to B. That's the first loop. And the EMF source is moving from minus to plus. So take note of this. Take note of this. Then our first junction that we have is C, point C. So I1 enters point C, then it leaves I2, then I3. It leaves I2, then I3. Then we have junction D. We have junction D, and at junction D, I2 and I3 are entering the junction. Then I1 is leaving, or I4 is leaving the junction. So you can label I4 here, leaving point D, to help in your solution. Then we have 3 resistors. 2 are connected parallel. Then 1 is connected to the combination of these 2 in series. So we have 2 resistors in parallel. Then the combination of them is connected to 1 in series. So now let's look at the solution of this problem. So there are 3 unknown currents in the circuit. So as we've seen earlier, we have I1, I2, I3. These are the unknown currents in the circuit. So we must obtain 3 independent equations for us to solve them simultaneously to get the unknowns, which then can be solved by substitution. Yes. So we can find the equations with 1 application of the junction rule, then 2 applications of the loop rule. So we apply just 1 junction rule. So we will pick point C. So we go back to the diagram, then we pick point C for the junction rule. Then we apply 2 application of loop rule. So we apply 2 loop rule as we saw in diagram, the one up there, then the one down there, close to the battery. So for the junction rule, point C will be chosen. Then the top and bottom loop is chosen as well. Both loops show the direction at which the circuit will be traversed mathematically. So both loops will show us the direction at which we'll be moving across the circuit for our loop. Then we apply the junction rule to point C. So when we apply the junction rule to point C, I1 is entering the junction, as I said earlier. I2 is leaving the junction. So we apply the loop, then we have an I1 will be equal to I2 plus I3. So this is your equation 1. I1 is equal to I2 plus I3. I1 is entering the junction. So the currents leaving the junction, you sum them up, then equate it to the current entering the junction. So this is your equation 1. So the diagram, we use this junction, then we use these 2 loops. We use these 2 loops. So you take note of that. Now from the bottom loop, it is traversed clockwise and generated equation with the loop rule. The generated equation with the loop rule is the potential difference across the battery, the potential difference across the 4 ohm resistor, and the potential difference across the 9 ohm resistor. So this is how the loop is. It's it's moving from A through to B, then through to this resistor, then through to this resistor. So now we are coming to apply the rules we learned earlier, the tricks in solving the problem. So if you look at here, across the battery, it is moving from A to B, and the EMF source is from minus to plus. Therefore, our voltage will be plus. Our voltage will be plus. But across the 4 ohm resistor, it's moving from B to A. It is moving from B to A. It is moving from B to A. So you can see it is in the direction of B to A. So therefore, it will be minus. And the 9 ohm resistor is also in the direction of B to A. So it will also be minus. But the voltage source is from minus to plus. The direction is from minus to plus. So here's the direction. And the direction here for the loop here is from plus to minus. So therefore, it will be negative. So for the two resistors, their potential difference across them will be negative. So for the 4 ohm, it will be negative. The 9 ohm, it will be negative, as we can see here. So the potential difference here from A to B is positive. The 4 ohm is negative. The 9 ohm is negative. So now here is our equation 3. Potential difference here is current times resistance. So here is the resistance for the 4 ohm resistor. Then the current I1. So I1 will pass through the 4 ohm. The I1 will pass through the 4 ohm. Then for the 9 ohm resistor, I3 passes through the 9 ohm resistor. So we multiply those quantities to get their potential difference. So this is our equation 2. This is our equation 2 for the first loop. Now the next loop is the top, the one in the parallel connection of the resistors, and it is traversing clockwise as well. So therefore, the equation that we will generate is, we sum up the potential difference across the 5 ohm resistor, then the potential difference across the 9 ohm resistor. So for us to get the potential difference is current times the resistance. But we have to apply the tricks here. So in the loop, our EMF source is moving from A to B, so minus to plus. But if you look at the 5 ohm resistor, it is from B to A. So the loop is like this, from B to A. Therefore, the potential difference will be minus. The potential difference will be minus. But if you look at the 9 ohm resistor, it is from A to B in the direction of the EMF, which is A to B. So it is in the same direction, therefore it will be plus. So we take note of these two. One is minus, which is moving from B to A. Then one is plus, which is moving from A to B. So therefore, we're having minus R I2. So I2 passes through the 5 ohm resistor. Then I3 passes through the 9 ohm resistor. So therefore, you take note of that. So the 5 ohm voltage will be minus, then the 9 ohm voltage will be plus. So this is our equation 3 for the second loop. Now let's bring them together, then solve them simultaneously. Stating all the equations, our equation 1 is I1 is equal to I2 plus I3. The equation 2, 4 times I1 plus 9 times I3 is equal to 6. So the 6 potential difference from the battery, we just made that one the subject because all of them was equal to 0 and that was minus, so we just brought this up. Then our second equation, or our third equation, is minus 5 times I2 plus 9 times I3. So we stated all the equations that we had from the loop and the junction rule. So let's solve them simultaneously. Firstly, from equation 3, making I2 the subject from equation 3, we sent the 9.0 times I3 to the other side of the equation. Then we divided through by minus 5.0, making I2 the subject. So I2 is 1.81 times I3. So this is our I2. So now we substitute I2 that we had into equation 1. We substitute I2 into equation 1. So this is our equation 1. So if you substitute I2 here, you're having I1 to be equal to 1.181 I3 plus I3. So we add this to our I1, then becomes 2.181 times I3. 2.181 times I3. So now we've gotten our I1, our I2, both having I3, multiplying them. So now if we substitute We substitute I1, which is equal to 2.18 I3 into equation 2. So we have an I1 here, so substitute it into this area. So we have this, then we multiply it by 4. So we make I3 the subject, then we divide through by that. Therefore, we have an I3 to be equal to 0.34 ampere, having I3 to be equal to 0.34 ampere. So now after that, we can find our I2. So we know our I2 to be equal to 1.81 times I3. So we substitute I3 into the equation. We're having I2 to be equal to 0.615 ampere. We're having I2 to be equal to 0.615 ampere. So therefore, we can also find our I2. We can also find our I1. So I1 is equal to 2.181 times I3. If you substitute I3 into the equation, we're having I1 to be equal to 0.742 ampere. Having I1 to be equal to 0.742 ampere. So this is how we use the Kirchhoff's rule to find current in a complex circuit having a lot of resistors, a lot of junctions, and a lot of loops in it. So here's a trial question that you can try your hands on and get your final answer, the current in the 10 ohm resistor in this circuit.